All right, hello everyone, and welcome to my channel. This is an educational channel. We look at different theories of everything, all-encompassing theories, paradigm shifters, things to help you with your awakening to 5D consciousness, building a holistic worldview. Today is our 488th video on the reciprocal system of theory from Dewey Bernard Larson. And Mr. Larson, in 1959, proposed his two fundamental postulates about how the universe operated, and then derived a theoretical universe from those postulates, what his universe would look like if his postulates were correct. And then in his work, he compares his theoretical universe with the measured empirical universe of the legacy scientists. And he does that here in this book that we're looking at today, called Basic Properties of Matter on Chemistry. Larson looks at many of the basic properties of matter, like the melting point and the compressibility and the interatomic distance, and compares them with the scientific tables. He derives equations for these values and plugs them into all of the elements and many molecules, and then compares. And it's an interesting study. We're about to start chapter 13 on electric charges. Quick note on the reciprocal system is that Larson is one of the few scientists to propose a universe of motion. The universe is not made out of matter, it's not made out of energy, but it's made out of motion. And specifically, it is made out of a kind of motion that Larson calls scalar motion. We just went over that last chapter, the last two videos. But if you want a more thorough rundown of the reciprocal system, before you start this, you might want to watch any of my first 474 videos on this subject, and then come back. You might still be able to glean quite a bit from Larson without such an intro, but it's there for you if you'd like. And we're going to get into chapter 13. It's called Electric Charges. One last thing is that Larson's reciprocal system is a theory of everything. It is a generalized theory, a system of theory, meaning that it applies to all subjects. And so we're looking here at chemistry, in particular here at electric charges, but that doesn't mean that this is irrelevant to anything else. His theory on chemistry, once learned, can be applied to his theory of astronomy, or his theory of metaphysics, or economics, or any number of other topics. It's a generalized theory, so you have to understand how the theory works, and then you can apply it to whatever subject you like. So, just because you don't like chemistry doesn't mean that you can't get anything out of this. Okay, chapter 13, Electric Charges. The history of the development of a mathematical understanding of electricity and magnetism has been one of the great success stories of science and engineering. With the benefit of this information, a type of phenomena totally unknown up to a few centuries ago has been harnessed in a manner that has revolutionized life in the more advanced human societies. But in a strange contrast, this remarkable record of success in the identification and application of the mathematical relations involved in these phenomena coexists with an almost complete lack of understanding of the basic nature of the quantities with which the mathematical expressions are dealing. In order to have a reasonably good conceptual understanding of electricity and magnetism, we need to be able to answer questions such as these. What is an electric charge? What is magnetism? What is an electric current? What is an electric field? What is mass? What is the relation between mass and charge? How are electric and magnetic forces produced? How do they differ from the gravitational force? How are these forces transmitted? What is the reason for the direction of the electromagnetic force? Why do masses interact only with masses, charges with charges? How are charges induced in electrically neutral objects? Conventional science has no answers for most of these questions. To rationalize the failure to discover the explanations, the physicists tell us that we should not ask the questions. Quote, the question, what is electricity, so often asked, is meaningless. That's from De Andrade. Another quote from Rudolf Carnap. What is electricity? Definitions that cannot, in the nature of the case, be given should not be demanded. The difficulty in accounting for the origin of the basic forces is likewise evaded. It is observed that matter exerts a gravitational force, an electric charge exerts an electric force, and so on. But the theorists have been unable to identify the origin of these forces. Their reaction has been to evade the issue by characterizing the forces as autonomous, fundamental conceptions of physics that have to be taken as given features of the universe. These forces are then assumed to be the original sources of all physical activity. So far as anyone knows at present, all events that take place in the universe are governed by four fundamental types of forces. That is a quote. I don't know by whom. As pointed out in chapter 12, the last chapter on scalar motion, this assumption is obviously invalid, as it is in direct conflict with the accepted definition of force. But those who are desperately anxious to have some kind of a theory of the phenomena that are involved close their eyes to this conflict. After having solved the problem of the origin of the forces by assuming it out of existence, the theorists have proceeded to solve the problem of the transmission of the basic forces in a similar manner. Since they have no explanation for this phenomenon, they provide a substitute for an explanation by equating this transmission with a different kind of phenomenon, for which they believe they have at least a partial explanation. Electromagnetic radiation has both electric and magnetic aspects and is unquestionably a transmission process. In their critical need for some kind of an explanation of the transmission of electric and magnetic forces, the theory constructors have seized on this tenuous connection and have admitted that electromagnetic radiation is the carrier of the electrostatic and magnetostatic forces. Then, since the gravitational force is clearly analogous to those forces and can be represented by the same kind of mathematical expressions, it has been further assumed that some sort of gravitational radiation must also exist. But there is ample evidence to show that these forces are not transmitted by radiation. As brought out in Volume 1, gravitation and radiation are processes of a totally different kind. Radiation is an energy transmission process. A quantity of radiant energy is produced in the form of photons. The movement of those photons then carries the energy from the point of origin to a destination, where it is delivered to the receiving object. No movement of either the originating object or the receiving object is required. At either end of the path, the energy is recognizable as such and is readily interchangeable with other forms of energy. Gravitation, on the other hand, is not an energy transmission process. The apparent gravitational action of one mass upon another does not alter the total external energy content, potential plus kinetic, of either mass. Each mass that moves in response to the gravitational force acquires a certain amount of kinetic energy, but its potential energy is decreased by the same amount, leaving the total unchanged. As stated in Volume 1, gravitational or potential energy is purely an energy of position. That is, for any specific masses, the mutual potential energy is determined entirely by their spatial separation. All that has been said about gravitation is equally applicable to electrostatics and magnetostatics. Each member of any system of two or more objects apparently interacting electrically or magnetically has a potential energy determined by the magnitudes of the charges and the intervening distance. As in the gravitational situation, if the separation between the objects is altered by reason of the static forces, an increment of kinetic energy is imparted to one or more of the objects, but its or their potential energy is decreased by the same amount, leaving the total unchanged. This is altogether different from a process such as electromagnetic radiation, which carries energy from one location to another. Energy of position in space cannot be propagated in space. The concept of transmitting this kind of energy from one spatial position to another is totally incompatible with the fact that the magnitude of the energy is determined by the spatial separation. As stated earlier, the coexistence of an almost total lack of conceptual understanding of electric and magnetic fundamentals with a fully developed system of mathematical relations and representation seems incongruous. In fact, however, this is the normal initial result of the manner in which scientific investigation is usually handled. A complete theory of any physical phenomena consists of two distinct components: a mathematical formulation and a conceptual structure, which are largely independent. In order to constitute a complete and accurate definition of the phenomenon, the theory must be both conceptually and mathematically correct. This is a result that is difficult to accomplish. In most cases, it is practically mandatory to approach the conceptual and mathematical issues separately, so that this very complex problem is reduced to more manageable dimensions. We either develop a mathematically correct theory that is conceptually imperfect, a model, and then attack the problem of reconciling this theory with the conceptual aspects of the phenomenon in question, or, alternatively, develop a theory that is conceptually correct as far as it goes, but mathematically imperfect, and then attack the problem of accounting for the mathematical forms and magnitudes of the physical relations. As matters now stand, In conventional science, the requirement of conceptual validity is by far the most difficult to meet. With the benefit of the mathematical techniques now available, it is almost always possible to devise an accurate or nearly accurate mathematical representation of a physical relation on the basis of those physical factors that are known to enter into the particular situation and the currently accepted concepts of the nature of these factors. The prevailing policy, therefore, is to give priority to the mathematical aspects of the phenomena under consideration. Vigorous mathematical analysis is applied to models which admittedly represent only certain portions of the phenomena to which they apply, and which, as a consequence, are conceptually incorrect, or at least incomplete. Attempts are then made to modify the models in such a way that they move closer to conceptual validity while maintaining their mathematical validity. There is a sound reason for following this mathematics first policy in the normal course of physical investigation. The initial objective is usually to arrive at a result that is useful in practical application, that is, something that will produce the correct mathematical answers to practical problems. From this standpoint, the issue of conceptual validity is essentially irrelevant. However, scientific investigation does not end at this point. Our inquiry into the subject matter is not complete until we, 1, arrive at a conceptual understanding of the physical phenomena under consideration, and 2, establish the nature of the relations between these and other physical phenomena. A mathematical relation that is unexplained conceptually is of little value toward accomplishing those objectives. It cannot be extrapolated beyond the range for which its validity has been experimentally or observationally verified without running the risk of exceeding the limits of its applicability. Nor can it be extended to any area other than the one in which it originated. As it happens, however, many physical problems have resisted all attempts to discover the conceptually correct explanations. Many of the frustrated theorists have reacted by abandoning the effort to achieve conceptual validity and are now contending that mathematical agreement between theory and observation constitutes, quote, experimental verification. Obviously, this is not true. Such a verification, or any number of similar mathematical correlations, tell us only that the theory is mathematically correct. As has been emphasized at several points in the preceding discussion, mathematical validity does not in any way assure conceptual validity. It gives no indication whether the interpretation that is being given to the mathematical relations is right or wrong. The inevitable result of the currently prevailing policy is to overload physical science with theories that are mathematically correct but conceptually wrong. Solutions for the many long-standing problems of physical science clearly cannot be obtained as long as the attacks on the problems are terminated when mathematical agreement is achieved. But even if this defect in present practice is corrected, it is doubtful whether the answers to most of these difficult problems can be obtained by the prevailing method of devising a mathematical solution first and then looking for a conceptual explanation. The reason is that a valid mathematical expression can be constructed to fit almost any model. As Einstein states the case, quote, it is often, perhaps even always, possible to adhere to a general theoretical foundation by securing the adaptation of the theory to the facts by means of artificial additional assumptions, end quote. Consequently, the mathematical expressions cannot be relied upon to furnish the necessary clues to a conceptual understanding. The important contribution of the reciprocal system of theory to the solution of these problems is that it enables attacking them from the opposite direction, that is, first arriving at a conceptual understanding by deduction from very basic, general basic relations, and then developing the mathematical aspects of the established conceptual relations. In other words, instead of getting a mathematical answer and then looking for a conceptual explanation to fit it, we start by getting a conceptual answer and then look for a mathematical way of expressing it. In general, this is a much simpler procedure, but it could not be utilized on any extensive scale until a unified general theory was available, so that conceptual answers could be obtained by deductive processes. The reciprocal system of theory satisfies this requirement. The clarification of the basic aspects of electricity and magnetism provides a dramatic example of the power of this new method of approach to physical problems. It is no longer necessary to deny the existence of answers to the questions listed at the beginning of this chapter, or to content ourselves with pseudo-answers such as the curved space explanation of gravitation. Two of these questions, what is mass and what is an electric current, have already been answered in the previous pages of this and the preceding volume. Those involving magnetism will be answered in the general discussion of that subject, which begins with chapter 19. And the processes of induction of charges will be explained in chapter 18. The answers to all of the other questions in this list will be developed in this present chapter. When those presentations are complete, we will have provided simple and logical explanations for every one of these items with which present-day science is having so much difficulty. In the universe of motion, all physical entities and phenomena are motions, combinations of motions, or relations between motions. It follows that the development of the structure of the theory that describes this universe is primarily a matter of determining just what motions and combinations of motion can exist under the conditions specified in the postulates. Thus far, in our discussion of electrical phenomena, we have been dealing only with translational motion, the movement of electrons through matter, and the various effects of that motion, the mechanical aspects of electricity, so to speak. We will now turn our attention to the electrical phenomena that involve rotational motion. As we saw in Volume 1, gravitation is a three-dimensional, rotationally distributed scalar motion. Objects having only one or two effective dimensions of scalar rotation were found to exist, but these objects, subatomic particles, have only a limited role in physical phenomena. In view of the general pattern of generating motions or greater complexity by combining motions of different kinds, the possibility of superimposing one-dimensional or two-dimensional scalar rotation on gravitating objects to produce phenomena of a more complex nature naturally suggests itself. On analyzing this situation, however, we find that the addition of ordinary rotationally distributed motion in less than 3 dimensions to the gravitational motion would merely modify the magnitude of that motion and would not result in any new kinds of phenomena. There is, however, a modification of the rotational distribution pattern that we have not yet explored. 3 general types of simple motion, scalar motion of physical locations, have thus far been considered. 1, translation, 2, linear vibration, and 3, rotation. We now need to recognize that there is a fourth type, rotational vibration. A motion that is related to rotation in the same way that linear vibration is related to translational motion. Vectorial motion of this type is uncommon. The motion of a hairspring of a watch is an example, and it is largely ignored in conventional physical thought, but it plays an important part in the basic motion of the universe. You know, so your rotational vibration is like that. So that is what Larson is saying, that is a charge. A rotational vibration is a charge. Now remember, in Larson's system, the electron is uncharged under normal circumstances. An electron can take a rotational vibration, but an electron by itself is a rotational unit of space. So an electron is uncharged as a rotational unit of space that moves through matter because the relationship of space to time is motion. You know, the universe is made out of motion. Motion is the relationship between space and time. And so an electron is a rotating unit of space. Matter is primarily made out of time. And so an electron can move through matter. But an electron can also acquire a rotational vibration, which is a charge. So the electron can be charged, but it is normally uncharged. Okay. At the atomic level, rotational vibration is a rotationally distributed scalar motion that is undergoing a continuous change from outward to inward and vice versa. As in linear vibration, the change of scalar direction must be continuous and uniform in order to be permanent. Like the motion of the photon of radiation, it is therefore a simple harmonic motion. As noted in the discussion of thermal motion in Chapter 5, when such a simple harmonic motion is added to an existing motion, it is coincident with that motion and therefore ineffective in one of the scalar directions and has an effective magnitude in the other scalar direction. Every added motion must conform to the rules for the combinations of scalar motions that were set forth in Volume 1. On this basis, the effective scalar direction of a self-sustaining rotational vibration must be outward, in opposition to the inward rotational motion with which it is associated. A similar addition with an inward scalar direction is not stable, but can be maintained by an external influence, as we will see later. A scalar motion in the form of a rotational vibration will now be identified as a charge. A one-dimensional motion of this type is an electric charge. In the universe of motion, any basic physical phenomena, such as a charge, is necessarily a motion, and the only question to be answered by an examination of its place in the physical picture is what kind of a motion it is. We find that the observed electric charge has the properties that the theoretical development identifies as those of a one-dimensional rotational vibration, and we can therefore equate the two. It is interesting to note that conventional science, which has been at so much of a loss to explain the origin and nature of the charge, does recognize that it is scalar. For instance, W.J. Duffin reports that experiments which he describes show that, quote, charge can be specified by a single number, end quote, thus justifying the conclusion that, quote, charge is a scalar quantity, end quote. However, in current physical thinking, this electric charge is regarded as one of the fundamental physical entities, and its identification as a motion will no doubt be a surprise to many persons. It should therefore be emphasized that this is not a peculiarity of the theory of the universe of motion. Irrespective of our findings based on that theory, a charge is necessarily a motion on the basis of the definitions that are employed in conventional physics, a fact that is disregarded because it is inconsistent with present-day theory. The key factor in this situation is the definition of force. It was brought out in Chapter 12 that force is a property of motion, not something of a fundamental nature that exists in its own right. An understanding of this point is essential to the development of the theory of charges, and some further consideration of the relevant facts is therefore appropriate in the present connection. For application in physics, force is derived by Newton's second law of motion, and it is the product of mass and acceleration, F equals ma. Motion, the relation of space to time, is measured on an individual mass unit basis as speed or velocity, v. That is, each unit moves at this rate. Or on a collective basis as momentum, the product of mass and velocity, mv, formerly called by the more descriptive name quantity of motion. The time rate of change of the magnitude of the motion is dv over dt, acceleration a. In the case of the individual unit, and in dv over dt are m dv over dt, force ma, when measured collectively. Thus, force is in effect defined as the time rate of change of the magnitude of the total quantity of motion, the quantity of acceleration, we might call it. From this definition, it follows that a force is a property of a motion. It has the same standing as any other property and is not something that can exist as an autonomous entity. Okay, we're going to stop there. Thanks for tuning in. Stay tuned for tomorrow. We'll finish this chapter. Have a good